Hello everyone, the problem that we're looking at today is finally a little bit more on level with what I'm doing right now, and it's the 2024 December contest gold problem 1 of Cowdependence. So yeah, it has the shortest problem statement and the longest solution. So we have n cows, and each cow, you can just read it yourself. This is so short. Just pause the video and read it, and yeah, it's actually pretty straightforward. But that's only the problem statement. The solution is not straightforward at all. It's probably one of the hardest problems that I've done last season when preparing for gold. So yeah. And you might be wondering why I did this problem last January 3rd to be exact, because, well, I failed the December contest and I just kind of wanted to challenge myself to see like how hard can it be. So I did the gold of that exact same contest, and it proved to me that, yeah, it is that hard. Anyways, the solution to this problem is actually very interrelated with the solution to the subtasks. Specifically, literally the final solution is just combining the code from subtask 2 and 3. And if you're sensitive about this algorithm, like if you've learned this, then just by me saying it's the combination of two solutions and looking at the constraint of this, you probably already know what the solution is going to be. And yes, it's called the square root divide and conquer, which is like, it is a type of divide and conquer, but the cap, the limit for this type of divide and conquer is adjusted according to the square root of the n of this problem. So let's take a look. First of all, let me pull up the solution that I wrote on Logu for this exact problem, which, I mean, I'd say I did a pretty good job, but maybe I didn't. So yeah, here this whole thing's in Chinese, so I might as well translate it. Okay, so yeah, just like other USACO problems, analyzing the first few parts is helpful, but this problem is different. The first few parts is like literally the solution, as I've said. So the first subtask is easy, literally just brute force. Second subtask is actually still pretty easy. I would say it's like maybe silver level. So second type subtask reveals that there are only 10 types of cows. So we can just process each type separately. That's basically literally what the subtask is asking you to do. So we can enumerate each type, and we just have to binary search to find at least how many you need for each of the X. So let's just take a look at my code, and it's honestly pretty straightforward. Except, obviously, you want to find how many groups you need. So you're gonna be able to know where is the position of the next cow with the same label. So at first I did a binary search for that, but that led to one of the test cases being TLE by like 1 millisecond, or was it 2? I don't remember, but yeah, it was bad. So I looked at the solution, and they have this stunningly effective little DP that's not even like a DP. It's just like pre-process where is the next position of the same label, and that makes this whole program guaranteed 500 milliseconds. So yeah, that's good. Yeah, so we have this very straightforward. Literally just process each group and see how process each label and see how many groups you need with this label. And by label, I just means like the type or whatever Farmer John calls cows. Label. Yeah, it is label. Okay, I guess it is label then. Okay, now let's look at the third subtask technically. So in this subtask, each group of cow can have at most 10 of them. Sorry. Each label, there's at most 10 cows with the same label. That's how we're gonna put it. So how do we solve this? Well, this is like arguably the hardest part, I would say, about this entire problem. Except for obviously knowing to combine subtask 2 and 3, this is the hardest part. So each type of cow appears at most 10 times, and we have a very important observation is that each group have to have at least one cow, which might seem obvious to you at first, but if you think about it, that means each cow label can make at most 10 different groups, which is going to make our lives a lot easier, because now we can kind of reverse psychology this. Thinking about it backwards, instead of thinking what is the minimum number of groups you must divide this into for a certain X, we think about what is the minimum X if we want to divide these cows into this many groups. And notice that this many groups that I just said can be at most 10, because each label can be divided into at most 10 groups. So this is how I implemented it. Actually, still pretty straightforward after you thought it through. So Yeah. Also, just to make it clear, the lab thing is label, and I just push back the label for alg 1 and alg 2, algorithm 1 and algorithm 2. So lab I for yeah. So alg 1 contains all the label of the cows that we need to process with the first algorithm, meaning that they have more than 10 in this label, and alg 2 is those with less than 10 in this label. I mean square root, not 10. Sorry, not 10 anymore. We're dealing with square root of n now instead of 10. So yeah, more than sqrt 10 in it, then it's algorithm 1. Less than sqrt n, then it's algorithm 2. And I'll explain why we can do that later, but just know that for now. So I is all the cows with at most sqrt n cows in this label. Yeah, or I call it cow type here instead of label. So we iterate through every single cow in this label. Now we iterate through how many groups we make out of these cow labels. And notice obviously it's at most lab I size, which is how many cows has this label. At most that. So we want to make J groups. And now we just have to know what is the least X we need to make J groups. So we just binary search to find that X. This whole thing is very much straightforward. You binary search the mid. If the mid does work, then you lower it. If the mid doesn't work, you make it bigger and until you find the optimal mid. And then we do this kind of like a prefix sum difference kind of thing. C is like a prefix sum array that tells you how many groups how many different labels, how many different groups require at least this X. So we take a prefix sum of it. So notice that L minus 1 is the least number of X we need to make J groups. So we increment C L minus 1 by 1. And also we have to increment every single N plus 1 by 1 for every single label because every cow label or cow type has to has a starting group. So this means that when X is N plus 1, there is one group from every single cow label. And then we just take the prefix sum, pretty straightforward. And yeah, I mean, that's the suffix sum, actually. Suffix sum. And then we just add the answer from the first to the second algorithms. And now we have to come back to the all essential question. Why does this work? Why can't we just divide and conquer like this according to the square root and it just runs in time? Except, I mean, it's supposed to, but my algorithm didn't actually initially. But why? So this is actually like a very smart trick that you just have to memorize and you can use it later on. It's the fact that there's at most square root n different cow labels with number of cows in it being greater than or equal to square root of n. Okay, I know that was a long sentence, so I'm just going to elaborate on that. So imagine a group has let's just call sqrt n square root of n, let's just call that x, okay? So imagine a group with at least x cows. You can have at most X groups with at least X cows, because otherwise the total number of cows will be greater than N. So with this being said, we know the second algorithm obviously runs in time because, well, we know that this group has less than the square root of N, which is X, so less than X cows in this group. But the first one also runs in time because we know that there's at most X labels that go to the first algorithm. So the time complexity of this whole thing is just N log n, which is the complexity of one run of these algorithms, times sqrt n, or x, as I've just defined it as. So yeah, this is it for this problem, and it's like stunningly smart, especially this little DP that the solution came up with, and also just everything else about it. And yeah, this is the way USACO is supposed to be, you know? Okay. Thanks for watching, and I'll see you tomorrow. Okay, a little grind report for today. I'm starting to realize maybe I'm kind of starting to lose it with like the grind spirit that I had last season. Like last season, I was able to grind 10 hours, 10 and a half hours a day, no problem. But now, like even if I have nothing else to do this whole day, like I literally didn't do anything else today, and I still only grinded for like what, 5 hours, which is very disappointing. I mean, it's partially because I woke up really late, but I also have to go to bed early today for a coding class tomorrow morning. But also just like I'm wasting a lot of time, which is not good. I mean, 5 hours still solid grind. I solved two problems. One of them is the recent U.S. Open Gold election queries, and the other one is symmetry, which is a computational geometry. So I mean, both of those are solid problems. I wrote a solution, but like 5 hours just for that, it's pretty low efficiency, and also just the fact that I just didn't actually get enough time in, or at least as much time as I would have hoped. So yeah, I'm just saving the code right now. Not great, but also I think I just need the urgency that I had last year. Like last year, I was just telling myself, if I don't make gold this season, my entire informatics and competitive programming career is just cooked, and like my life is basically cooked too. And now I'm just not feeling that urgency, so I got to like push myself. I need to tell myself that if I don't make platinum, I'm cooked for every other Olympiad that I need to grind for instead of this thing. Like I need to deal with USACO and get over with this season, like in the next 3 months, and then I can spend all my time on USAFO or maybe other stuff. So yeah, thanks for watching, and I'll see you tomorrow.